So now to writing up the normal equations in exercise 1b, we want to minimize this expression here. So we want to find the A0, A1, and A2 that construct the theta tilde. And we want to minimize this expression here based on x bar, the data being x, respectively x multiplied by x minus 1. So first of all, let us just figure out what are the corresponding variable names in our case compared to the general case for the normal equations. So we start by looking at the x in the general case for the normal equations. For us, this x is equal to theta. And if we look at the m here, it is the number of data points. So for us, this m is equal to 2 because we have 2 data points in our data. And that means we will have to write up 3 equations. Now, their y1 is in our case equal to x, whereas their second data point y2 is in our case equal to x multiplied by x minus 1. Do we need any more information? Well, no. I mean, it's also nice to just establish that the thing that is called y hat in the book's case is in our case called theta tilde, and we express it using a0 plus a1 multiplied by x plus a2 multiplied by x minus 1. But I mean, apart from that, that is all that we need to write up the normal equations. So let us just start from one end for these normal equations. We want to write the first one up here using our notation. So we have the mean of theta has to be equal to a0 plus a1 multiplied by the mean of x plus a2 multiplied by the mean of x multiplied by x minus 1. So that was our first equation. Now we can continue to the second equation. I mean, the reason why there aren't more terms is because we only have 2 data points. So we can continue to the second equation, which has to be the covariance, and we write the covariance of theta and their y1 is in our case equal to x, so of theta and x has to be equal to, and here we have the sum of a1 multiplied by the covariance of y1, which for us is x with itself, so that's covariance of x and x, plus a2 multiplied by the covariance of the second data point, x minus 1, and the first data point. And that was the second equation. And then we have the last equation, the third equation. We only have 3 equations because we only have these 2 data points. So the covariance of theta and the second data point, which is x multiplied by x minus 1, that has to be equal to a1 multiplied by the covariance of the first data point with the second data point, plus a2 multiplied by the covariance of x minus of the second data point with itself. So it's actually, when you take the covariance of something with itself, it is essentially just its variance, right? And we can also just note that the covariance of x and x is also just the variance of x. So we will have to calculate a bunch of different stuff here in order to make this work. Let's just put a ring around the stuff we need to calculate. We need to calculate the mean of x. We need to calculate the mean of x multiplied by x minus 1. We need to calculate this covariance and this covariance, the variance of x, this covariance. We don't need to calculate this covariance because these 2 covariances are the same, but we also need to calculate this variance. So we'll need to calculate all in all 7 different things. Now let's just start from, let's just say the easiest first, because we already know some of this stuff. the mean of x is m1. We did that in 1a. And we also know the variance of x, so I can just put a little check here. And the variance of x, what was that? That was the covariance of x with itself. We also know that. We also know the covariance of theta and x. So we know 3 of these 7 things. Essentially, we only need to calculate 4 things. So let's get started. Where do we start? Where do we start? Where do we start? Where do we start? Boom, 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 boom. Let's get started. We can try and take a look at the mean of x multiplied by x minus 1. Now, this is, again, using the double expectation property. This is the mean of x multiplied by x minus 1 given theta. Then we can take the expectation of that, and double expectation property gives us that this is equal to this. Okay, we know that x given theta is Poisson distributed, and here we're taking a function of x given theta, which is x multiplied by x minus 1. And we know from the hint in the book that the innard here is just theta squared. And this is m2. So now we have also taken care of this one here. The next one that we will look at is the covariance of theta and x multiplied by x minus 1. Now, by definition of covariance, this is equal to the mean value of theta multiplied by x multiplied by x, multiplied by x multiplied by x minus 1 minus the mean of products, the product of the means of theta and x multiplied by x minus 1 respectively. So the second term isn't that hard because I know that this is equal to m2 and this is equal to m1 by definition. The first term here, I can tackle that by using a double expectation trick again, where I can see that if I condition on theta inside, then I am allowed to take out what is known, so I'm allowed to take theta outside. And what is left, well, what is left inside is just the mean of x multiplied by x minus 1 given theta. So the inside is just it is just theta squared because this thing is Poisson distributed. X given theta is Poisson distributed. So I have the mean value of theta to the third minus m1 m2, and this gives me m3 minus m1 m2. And then I have also calculated the covariance of theta and x multiplied by x minus 1. To the next. Okay, so now I've also taken care of this one. Now I need to take care of these two. So I'll just start with the least scary one, which is the covariance of x multiplied by x minus 1 with x. And the reason why this is the least scary one is because this variance is the covariance of this with itself. So, I mean, this is the least scary one, definitely. Which tricks can we use here? Well, let me just plug in the definition of covariance. So I have the mean of the products, which is x multiplied by x multiplied by x minus 1. And then minus the product of the means, which is the mean of x multiplied by the mean of x multiplied by x minus 1. I know that the first one here is just the mean of theta, which is just m1. And the second one here, we've already established, is just m2. So the first term is what's giving me the problem. And again, I can use the trick of double conditioning on theta. And I kind of use another trick here, bear with me, where I say I take one of these x's and I minus 2 and then I add by 2. So then condition on theta, minus m1, m2. Now, the reason why I do this is because while I do not know what the value of the mean of this given theta is, I do know that the decreasing factorials, in the sense that the mean of x multiplied by x minus 1 multiplied by x minus 2 given theta, well, I do know what this thing is by the hint that's given in the exercise. And by linearity of conditional expectation, what I have in the next term is the mean of x multiplied by x minus 1 given theta multiplied by a 2, which comes from this plus 2 here, minus m1, m2. Now, based on the hint for Poisson distributed factorials, stuff like that, this first term inside the condition is just equal to theta to the third, whereas the second term is equal to 2 multiplied by theta to the second. And then I can just use linearity of the normal expectation to achieve my result, which is m3, to attain my result, which is m3 plus 2, m2 minus m1, m2. Now, basically, I can take this trick that I just used and apply it on the variance of x multiplied by x minus 1. So let's also take a look at this variance, x multiplied by x minus 1. You know what? You can do this calculation on your own, because this video is getting way out of hand. It's getting way too long. So just try to do this on your own and achieve and get the result m4 plus 4 m3 plus 2 m2 minus m2 squared. Yeah, it's a good exercise. And if you don't get that, you can always look at the PDF solutions. Okay, so now we've also calculated, well, calculated this, and I wrote what this is. So now we have all of these different things. And the next step would be to plug all of these expressions into this equational system. So just because it's kind of nice to wrap this up with an actual equation system, let's also just plug everything that we just found inside these three equations. So let's just start with the first equation. We had mean of theta, that's m1, has to be equal to a0 plus a1 multiplied by the mean of x, which was m1, plus a2 multiplied by, what did we have up here, multiplied by the mean of x multiplied by x minus 1, and that is a2 and 2. And the next equation, we had the covariance of theta and x on one side, and we've calculated that. And then we have a1 multiplied by m1 plus m2 minus m1 squared. So this is just the plug-in for the variance of x. And then we also plug in a2 multiplied by the covariance of x and x minus 1, which is m3 plus 2 m2 minus m2 m1. And then we have our last equation, which on the left-hand side has the covariance of theta and x minus 1, and on the other hand has a1 multiplied by the covariance of x and x minus 1. So this, and at last has a2 multiplied by the variance of x minus 1, which was something that I was too lazy to calculate and told you guys to do on your own. So here, so this is the system of equations that govern what A0, A1, and A2 should be. Now, depending on the exact values of M1, M2, and M3, then this will either have a unique solution, no solution at all, or maybe have multiple solutions. It's kind of hard to say a lot about this right now because we don't really know exactly which values the M's they take, and depending on the different values they take, they could cancel each other out or do weird stuff that we cannot really predict. And that is also one of the reasons why we wrote up the normal equations instead of just calculating the linear estimator using one of the formulas in chapter 6.1. But however, these are the equations that govern the second order polynomial Bayes estimator of the data x.